Thank you, Dr. Enright, for that introduction, and thank you also, Professor Shakmar, for your opening statement today, setting the scene for this day of climate change presentations focused on the challenges facing Australian agriculture in the future. Today, I'll be setting the scene for you in terms of looking at the historical changes that we've seen in climate and attributing the changes in agricultural production that we've seen to those historical changes. I'll also be talking about the likely future projections and the likely impacts that that will have on Australian agriculture as well. When I give these presentations, I do like to start with an animation of global monthly temperature anomalies, because I think this really gives us a sense of the extent of change that we've already seen in the historical record. So what you'll see very shortly when I press the animation button to start is the monthly temperature anomalies. So these are departures from a long-term mean from the period 1880 right through to almost present day. What you'll see is, you'll see in the earlier part of the record both warm and cold monthly anomalies, and as the animation progresses you'll see that there is a change, and a significant change, in those monthly temperature anomalies. So I'll start the animation now. So, as I said, in the earlier part of the record, you've got a balance of cold anomalies and warm anomalies. But as we move through the historical record towards the present day, what you do see is that the frequency of those cold monthly anomalies starts to decline, the size of those anomalies starts to shrink, and the size and frequency of the warm anomalies start to increase. And so that when we get to the most recent part of the record, you can see there that there's only 1 month in that entire period where the monthly temperature anomalies at a global scale are slightly below the long-term average. And you can see in some instances, particularly in the most recent decades, that the average temperature anomalies at the monthly scale are in excess of 1 degree, 1.5 degrees. In fact, in some instances, we're almost 2 degrees warmer than the long-term mean. So what we can see is that there's been significant change in the global temperatures. We've also seen changes in Australia in the same vein. And so if you pay attention to the top map on the left-hand side, this is a map produced by the Australian Bureau of Meteorology showing trends in the average temperatures. And you can see that over almost the entire of the continent, temperatures have been warming, and probably warming more significantly over the Australian East Coast region than the West Coast. 2019, though, was the hottest year on record in Australia, and that was 1.5 degrees warmer than the long-term mean. That in 2019 was a year that had several months with heat waves and several records, consecutive days with temperatures in the very high, sort of almost 41 degrees to almost 42 degrees. These consecutive heat days were actually records that were set last year. The other thing that's happened is that we've had a 5-fold increase in extreme heat events since the 1950s. And so a significant increase in those frequency of particularly destructive hot temperatures. In terms of the trends in Australian rainfall, on the bottom right-hand side of the slide, what you can see there is that both the West Coast and the East Coast have experienced significant declines in annual rainfall. And much of these declines are being driven by declines in winter and spring. In terms of temperature extremes, this map here shows you a comparison of temperatures in excess of 37 degrees Celsius and compares two periods. The first period is 1951 to 1980, and the second period is 2010 to 2018. And what you can see there is that almost the entire continent has experienced an increase in the frequency of days above 37 degrees. And we can see that in some instances, those increases have resulted in anywhere between 15 and 20 more days above 37 degrees over the most recent part of the historical record. So it's not just the extreme hot temperatures that we're seeing changes in, but we're also seeing changes in the extreme cold temperatures. And these two maps here show you the two extremes. So on the right hand side, we have the occurrence of temperatures below 2 degrees at the Stevenson screen. And so we sort of define these as the starting point for which frosts can actually occur. And so if you look at the coloration on the map there, the blue areas show where those temperatures of 2 degrees are actually occurring later and later in the calendar year. And whereas the orange to red show where those extreme minimum temperatures are actually occurring earlier in the year. So what we can see is, despite the warming that's actually occurred in the historical record, extreme minimum temperatures are actually occurring later in the year. And in some instances, the actual frequency of those events has increased as well. But on the other side of the spectrum, the very extreme hot days, and these are temperatures above 32 degrees, what you can see is that the occurrence of the first temperatures above 32 degrees are actually occurring earlier in the calendar year. And so we have this situation where we have frosts occurring later in the year and these extreme heat events actually occurring earlier in the year. So if we're thinking about an optimal flowering window, we are seeing that that is actually shrinking. And some work by a colleague at CSIRO, Dr. Fernanda Drecker, actually provides some estimates of the changes that we've seen in what could be classified as a sort of optimal flowering window. And you can see that there's very significant trends occurring across much of the southern parts of Australia, particularly in Western Australia. That trend is almost a shortening of the optimal flowering window by a day a year since 1970. And across on the East Coast, similar trends or similar magnitudes of trends, but also slightly smaller trends, but also in that shrinking of the flowering window. Excuse me. So what impact has this narrowing of the flowering window actually had? We can look at this through looking at observational data, or we can actually look at this using model data. So the first map that I wanted to show you is the modeled information and model data for wheat production across the Australian wheat belt. And this is some work that was produced by colleague Dr. Svi Hockman and his colleagues at CSIRO. And what it shows is the change in the sort of potential yields that have actually occurred since the 1990s. And this is based on responses entirely to climatic conditions. So in the model simulations, there are no nutrient limitations, there's no pest and disease. So what you're seeing here is the translation of the impacts of climate on production. And in the simulations, you can see that the potential yields have declined by about 27%. So on average from 4.4 tonnes to about 3.2 tonnes per hectare. Most of that is being driven by rainfall decline. So you can see 83% of those declines are attributed to the changes in rainfall that we've seen historically, and 17% are in response to both the increase in frequency of the minimum temperature extremes and the maximum temperature extremes, so the heat and the cold. But we can also look at the impact in a more aggregated way, looking at the observations. And this is some work by colleagues from ABES, and what it shows you is the impact of the climatic conditions that we've seen historically on broadacre agriculture. So this isn't just an individual crop, but is looking at a range of broadacre crops across the cropping belt. And very similar pattern of decline as presented in the simulation data in the previous slide. But you can see over the period 2000 to 2015, the production of broadacre agriculture has declined by, in some instances, in the very dark red areas at the top of the sort of Western Australian wheat belt, by as much as 20%. Because of the changes that we've seen in historical climate. But you can see across the entire wheat belt, there have been changes of the order of between 2% decline up to that 20% in the very dark red colours. So in response to those changes in historical climate conditions, we've also seen geographical shifts in the areas in which cropping is actually undertaken. And in this map, which is also produced by Neil and his colleagues, it shows the density of cropping that has actually occurred on average by comparing those two different periods, 2000 to 2015, against that 1989 to that 2000 period. And so you can see that what's happening is those blue areas are where cropping density has increased, and the red areas are where the cropping density has decreased in response to those temperature and rainfall changes. So just to recap then, we've seen that there have been some very significant changes in our historical climate, and that has already resulted in some significant impacts on Australian agricultural productivity, and that I've hopefully sort of shown you in terms of the previous few slides. What I wanted to do now was actually talk about the future, and to give you a sense of the extent of change that we might expect to see by 2100. And so this sort of rainbow diagram here actually tries to capture the amount of temperature change and associated emissions historically, which is the sort of black squiggly line that you see on the left-hand side of the graph. And then the sort of rainbow array of colors shows you the likely emissions pathways or representative concentration pathways, and the resultant temperatures that those RCPs might result in by 2100. So unfortunately, our current trajectory, where we're currently tracking, is on the RCP 8.5, so that red trajectory at the top. And that, as you can see, commits us to almost, well, anything between 3 and 5.5 degrees, almost 6 degrees of warming by 2100. If we think about the Paris Agreement commitments, so those voluntary commitments, if every country were to actually adhere to those voluntary commitments, which they're not at the moment, then that might bring the actual temperatures down to anywhere between 2.5 to almost 4 degrees of warming. And many of you have probably heard of the sort of threshold that many scientists are talking about, trying to cap warming at 1.5 to 2 degrees. And you can see that in order to do that, emissions would have to drop considerably over the next few years in order to keep us below that 1.5 to 2 degrees Celsius target. So where will we end up in the future? Well, that really depends on our trajectory of emissions going forward. At the moment, we are on the very top end of that those emission trajectories, but if there is collective action taken at a global scale, we may be able to successfully bring those emissions down, but where we actually get to really depends on the extent of action. So if we think about the likely temperature changes we might see across the globe, the way that we do this is by looking at or using climate models. And our global climate models, if those are initialized with those different emission scenarios, they provide us with different rates of warming, different rates of rainfall change, and other different climate variables for the future. These two maps here show you the likely global temperature change if the RCP 8.5, which is the trajectory that we're currently following, is continued out to around 2030 and to later in the century, near that sort of 2090 or period. And if we look at the short term for Australia, based on this sort of consensus of warming, we see that temperatures could be, by 2025, could be another 0.5 degree to 1.5 degrees for an RCP 8.5 emissions trajectory, or they could be up to 4.5 degrees warmer. So that's in addition to what we've currently experienced. If we look at the likely temperature change, rainfall changes, this map here shows you the consensus from a range of different global models, but it expresses the change in precipitation as a percentage per degree of global warming. So this map would suggest that for every degree of global warming, Western Australian rainfall may decline by anything from, say, 4 to about 6 or 7%. So that's for every degree of additional warming that we see. And what you can see is that there are some regional sort of winners and losers, if we want to define it in that way, in terms of rainfall change. So the Southern Hemisphere tends to be a region where rainfall declines over most of those continental land masses. And so agricultural production in the Southern Hemisphere certainly will become a more challenging prospect. These maps here show you the likely changes in rainfall and in drought conditions. So these are produced by the CSIRO, and the left-hand side map shows you the likelihood of increased incidence the left-hand map shows you the change in rainfall patterns and shows you where there is confidence that both winter and spring rainfall will decline. So those areas highlighted in that sort of orange color. And on the right-hand side, it shows you the frequency of drought conditions. And the orange shows you where there's a sort of a medium confidence that there will be an increase in the frequency of droughts, and the red is where there'll be significant confidence that future drought conditions will increase in frequency. So if we take these temperature and rainfall projections and try and understand the implications for agricultural productivity both globally and in the context of Australia. We need to use crop models or economic models that give us a sense of what those impacts are. This is a sort of a set of aggregated results for a range of different crops across the globe, and shows you that in response to the southern hemisphere sort of rainfall declines, that agricultural productivity is likely to be lower across much of the southern hemisphere, and that's of the sort of order of 3 to about 7% for the sort of mid part of the century. In the northern hemisphere, the prospect of increased production is simulated because of the removal of some of the temperature constraints currently existing on crop production. A detailed analysis by ABARES, this is a slightly older analysis now, but one that's relevant for the Australian context, shows you the impact of future changes in temperature and rainfall on wheat production on the top left-hand side, sheep production in the top right-hand side, and beef and wool production in the bottom left and right, respectively. The sort of the coloration scheme, or the color scheme, any colors that are pinks through to sort of reds and browns, showing where declines in productivity are very likely. The blues and greys and blues show where productivity potentially could increase. But I think what you can see there is that without significant adaptation or change, the agricultural production in the context of Australia is going to be more challenging in the future. So the question is, how do we begin to establish adaptation strategies for these changes? And at the moment, our focus has really been on trying to ascertain what the future changes in rainfall and temperature and crop suitability, etc., will be. We've also looked at sort of biophysical modeling, but what is missing from the development of these adaptation strategies and scenarios are more effective economic analyses to show what the impacts are of climate change with and without adaptation. But most importantly, we need to understand what the social ramifications are for our Australian farming communities. And we really need to do that in order to build the resilience of those communities to future climate change. And so all of these different dimensions are very, very important if we are to establish successful adaptation strategies going forward. When we think about adaptation, I think we need to see it as a sort of set of a hierarchy of options, and we talk about tiers of adaptation. So at the very lowest tier, we talk about this as incremental adaptation or incremental change or tactical change. So these are really small modifications of existing management. And some examples that you can see there are things like changing varieties or changing planting times or row spacing or looking at stubble retention or different ways of managing water. So these are all fairly small changes to existing practice. They are a lower risk, they're usually of a lower cost, but the problem with those is that they're successful for fairly small changes in temperature and rainfall, but become less successful as we move towards more extreme changes in both temperature and rainfall. So to cope with those more extreme changes in the projected rainfall and temperature, we need to think about the systemic or transformational adaptation options. These are more expensive, these are more risky, but they're likely to give us resilience to the larger or more extreme projections of rainfall and temperature that I discussed earlier. So the question that I'm often asked is, how much time do we have for action? And we have a very strong, almost linear relationship between the emission scenarios, the rates of accumulation in greenhouse gases, and global temperatures. And so what we can start to do is extrapolate the existing trends in the emissions and to give us some sense of when we might meet or surpass critical temperature thresholds. So if we say we have a 1.5 degrees Celsius goal and we want to cap emissions to prevent us from exceeding that goal, then we can use the sort of linear relationship to actually work that out. And so if we want to have a 50% chance of keeping temperatures below 1.5 degrees Celsius until the end of the century, we can only emit a further 480 gigatons of CO2, and that's from 2018. So based on the current rates of emissions, that really only gives us 9 years or a decade before we have to take some very significant and decisive action. So we could think about using this current pandemic as a catalyst for either thinking about how we start to try and address our emissions trajectories in a significant way. Otherwise, what we will see is, as our economies recover, we'll see that the emissions then continue and recover in terms of their trajectory very, very quickly. So we have an opportunity now to think about how we might, at a global scale, try and tackle the issue of greenhouse gas emissions. So just to conclude my presentation, what I hope you've taken away from the presentation today is that climate is already changing. It's changing here in Australia and globally, and more change is certain. We're seeing a range of climate variables change in directions that make agricultural productivity more challenging, or maintaining agricultural productivity more challenging. And those changes in extremes that we are seeing are ones that have significant impacts on our productivity. So I think a priori, what we can say is that given the historical trends and the future projections, agricultural production globally and in the Australian context will be far more challenging. And these are challenges that we can begin to address both through managing our emissions, but also through adaptation. So there's both mitigation and adaptation that will be the solution to this significant challenge. So I thank you for your attention, and I wish you success for the rest of the day. Thank you very much.